Okay, hello everyone. Let us now proceed to case number 2, repeated real roots. Okay, so we have a second order equation right here with constant coefficients. And we know that the auxiliary equation for this is a m squared plus bm plus c is equal to 0. Now, if we have repeated real roots, we know that m1 is equal to m2, right? And also, um, the determinant b squared minus 4ac is equal to 0. Now let's just take note of this because we will be using this at the latter part of this video. Okay, so what do we do if we have a second order equation and we can only get one solution? So we know that for a second order equation, we need two linearly independent solutions to generate the general solution, right? Okay, so what are we going to use? We're going to use the reduction of order method. Okay, so we are going to apply that here to the general case. And the general solution format that we will derive here, we will be using to an example later on. Okay, so let's start applying the reduction of order method. So we already have y1, which is e raised to mx, right? We know that this is the form of our solution. So in order to find y2, um, we know that y2 is mu multiplied by y1, right? Mu multiplied by y1, where mu is a function because y2 and y1 are linearly independent. Okay, so let's rewrite y2. This is equal to y2 is equal to mu raised to multiplied by e raised to mx. Okay, so let's get the first and second derivative of y2 first before we substitute it to our original equation here. Okay, so let's get that. So y prime is equal to mu prime e raised to mx plus mu m e raised to mx, right? Then what about y double prime? Y2 double prime, we have here mu double prime e raised to mx plus mu prime m e raised to mx, and then plus mu prime m e raised to mx. So these are like terms, and then plus what do we have here? Mu m squared e raised to mx. Okay, so let's simplify this by adding the like terms. E raised to mx plus 2 mu prime m e raised to mx plus mu m squared e raised to mx. Okay, so we will be using this one, and also this one. Okay, so let's substitute it to our original equation. So we will get a multiplied by mu double prime e raised to mx plus 2 mu prime m e raised to mx plus mu m squared e raised to mx, okay, plus b times mu prime e raised to mx plus mu m e raised to mx, then plus c multiplied by y, which is mu e raised to mx is equal to 0. Okay, so there we have it. If we distribute this, so we will get a mu double prime e raised to mx plus 2a mu prime m e raised to mx plus a mu, right, m squared e raised to mx plus b mu prime e raised to mx plus b mu m e raised to mx plus c mu e raised to mx is equal to 0. Okay, so this is very long, but we will simplify this. So let's start simplifying. So let's focus on these terms right here. The terms with the mu right here. Okay, so let's group them first here. Let's group them. We have a mu m squared e raised to mx plus b mu m e raised to mx plus c mu e raised to mx is equal to 0. Okay, so if we factor out mu, we will get a m squared e raised to mx plus b mu b m e raised to mx then plus c e raised to mx is equal to, oh, there's no equal to 0 here. We're just simplifying. Okay, so if we take a look, if we go back to our um, original equation, so we know that y1 is equal to e raised to mx is a solution of this, right? Is a solution to this. Now, if we substitute y1 in its derivatives to the original equation, it will look like this one, right? So if this is equal to 0 right here, then this should also be equal to 0, right? So this will evaluate to 0. So therefore, these three terms right here uh, will be simplified to 0. So okay, so we will be left with a mu double prime e raised to mx plus 2a mu prime m e raised to mx plus b mu prime e raised to mx is equal to 0. Okay, so there you have it. This is a lot simpler now. Okay, so let us factor out. If we divide both sides by e raised to mx, we will be left with a mu double prime plus a 2 times a mu prime plus b u prime is equal to 0. Okay. Now, we can now apply the reduction of order method, right? So let's let w be equal to mu prime. So we have a w prime plus 2a w plus b w is equal to 0. Now, let us separate the variables. So a w prime is equal to negative 2a w plus b w. Then if we factor out, if we divide both sides by w, we will get a w prime all over w is equal to negative 2a. Oh, wait. Seem to be missing something here. Um, so this is 2am. So this is 2am. Okay. So we also have 2am right here. Minus 2am plus b. Okay. This is also minus b. So this is also minus b. Okay, so before proceeding, before we integrate, let us simplify this right-hand side first. Okay, now for repeated real roots, we know that b squared minus 4ac is equal to 0, right? So if we try to use the quadratic formula to get m, so you will get a negative b plus minus b squared minus 4ac all over 2a, right? So since we know that b squared minus 4ac is equal to 0 for repeated real roots, we will get m is equal to negative b all over 2a. So if we plug this value right here, we will then get um, a over a w prime over w is equal to negative 2a multiplied by negative b over 2a minus b. So this will evaluate to, this will cancel out. You will be then left with a positive b minus b. So this will be equal to 0, right? So therefore we have is equal to 0. So now it is definitely a lot easier. Okay, so if we integrate this, okay, so let's format it first. A over w, and w prime is dw over dx, right? Is equal to 0. Now, if we multiply both sides by dx, we will then get a over w, dw is equal to 0. Let's just write dx here. Okay, so let's integrate this. So if we integrate, we will then get ln w is equal to c. Okay, so let us simplify. Let's find w by using the inverse property of logarithms. So we have w is equal to e raised to c, or let's just write it as c. Okay, so our main goal is to find u, right? Mu. So we know that w is equal to mu prime. Okay, so this is equal to d mu over dx, right? Is equal to c. Okay, so if we multiply dx to both sides, we will get d mu is equal to cx, right? So if we integrate this, we will then get mu is equal to c1x. Oh, what's this? dx. So this will be c1x plus c2, right? Now, these c1 and c2 are arbitrary constants. So for simplicity, let's just let c1 is equal to 1 and c2 is equal to 0. So our mu here um, will be equal to x. Okay, so we are now very close to our general form. So now that we know that mu is equal to x, so from the formula, you know that y2 is equal to mu multiplied by e raised to mx, right? So let's just do that. So what we have right here, so y2 is equal to mu multiplied by e raised to mx. So this will be our second solution. Now, in order to arrive at the general solution, we must get the linear combination of our two solutions. So, or let's write this as mu, instead of writing it like that, x e raised to mx. So this is our final solution. Okay, so our general solution will be y is equal to, so what is our first solution? What is our first solution? That will be c1 multiplied by, so this is y1, right? So y1 is equal to e raised to mx plus c2 multiplied by our y2, which is x e raised to mx. Okay, so there you have it. So for if we have repeated real roots, if we are given a problem with repeated real roots, we do not need to perform reduction of order method again. So we already did that for the general case. And then let's just take a look at this formula right here and apply it directly. So in the next video, we're going to do just that. Okay, so thank you for watching. And I hope you learned something, and see you in the next video.